Our speaker is Dimitris Gerontogiannis. Now from IMPAN, and the title of this talk is the log-Laplacian Ahlfors regular spaces in non-commutative boundaries.
Thanks. Thank you a lot for the invitation. Yeah, it's really nice to be at IMPAN. I'm for 2 weeks here and already have made quite a few connections and talking math. It's a very vibrant, place. So this work is about a Laplace type operator on spaces, on metric measure spaces, that seems that one can do analysis, kind of harmonic analysis, but they don't have to be smooth to have a differentiable structure or even an algebraic structure. And this talk, the log term in the Laplacian comes because we don't want the Laplacian to have very fast growing eigenvalues. As I would explain, this allows us to use it to study dynamical systems. For instance, group actions on these metric measure spaces, which are not necessarily isometric. Okay, so this work, the main part, the first part that I will present today. Did I close it? No, it just doesn't work now.
Does it work?
Yeah. There's no battery, it says.
There is no battery.
Yes, but I have one.
Okay.
So.
There are some batteries here, maybe I can try those. Or maybe we can go with yours as well, if you want.
Yeah, sure, I'll just put that. And then it should work. No? Also that. Yeah, no
Still
batteries.
no? No batteries.
Yeah. So maybe you just change the batteries at yours. And,
Okay, let's see. Oh, yeah.
Okay, that's good. Thanks for the batteries. I will put them back in. Okay, so the first part of the talk is joined with Bram Mesland from Leiden University in the Netherlands. But first, I should tell you what Ahlfors regular spaces are, but probably there are more experts here than I am on those spaces. The idea is that you have a metric. Here we will focus on finite measures. And you want a compatibility of the measure here with the metric. That the measure around any ball of radius r is of order r to some exponent delta. And as soon as we have this, then this delta coincides with many fractal dimensions. The Hausdorff, the box counting, and Aswad dimensions that are related to embeddings, and so on. So for this talk, delta, you can just think of it as the Hausdorff dimension. Although it seems like a strong requirement, there are a plethora of cases that have this structure. You can take compact Riemannian manifolds, even with boundary, if you can have them, the volume. measure will be Ahlfors regular. Several fractals in Euclidean spaces. The Hausdorff measure is Ahlfors regular for some dimension. Like limit sets satisfying the open set condition. Iterative functional systems and the limit sets of them. Now, Smale spaces is a generalization in the topological setting of axiom A systems, and on those one can build some kind of visual metrics with respect to which the measure that maximizes the topological entropy becomes Ahlfors regular. Moreover, for several hyperbolic groups, the Gromov boundaries admit an Ahlfors regular measure, the Patterson-Sullivan measure, and also for several Kleinian groups, their limit sets also are equipped with a Patterson-Sullivan measure, which is Ahlfors regular. Okay, so this is the setting that we want to create a harmonic analysis framework. And here, in this slide, I will try to explain to you why we care about such an operator that I call the log-Laplacian. But first, let's go to the manifold setting. Pick a manifold, a compact Riemannian manifold with the Riemannian distance and the volume measure. And now we have the Laplace-Beltrami operator, which is defined, let's say, on the smooth functions. Now we know that delta is essentially self-adjoint. This really means it's an unbounded operator. And you define it densely on L2. So essential self-adjointness means that it has a unique self-adjoint extension whenever you define it first on the smooth functions. Okay? And this really reflects the niceness of a smooth manifold. Moreover, this operator sees quite a lot of the geometry of the manifold. Its spectral properties, for instance, you can see that 1 plus delta to the minus d, you need to put 1 here to be able to invert it, because delta is 0 on constant functions. Okay, so you put 1, you push the spectrum a bit, and then you can invert it. And you can see that it is trace class operator if and only if t is greater than the topological dimension of the manifold over 2. Okay. And
What do you mean by trace class?
trace class,
Trace?
yes, you take the trace of the operator. Yes, exactly.
Sorry, when you write commutator delta with gamma,
What do I mean? I mean you take a representation that's any isometry. You take the isometry group of the manifold, and then you can view it as a unitary operator on L2 of X.
so gamma is principal. In principle, is acting on L2 at least.
Yes.
And preserves the domain.
Yes, exactly. You need to preserve the domain because it's unbounded. Exactly. Yeah, I hide, many details under the carpet, but we catch. And you can see that it is an isometry if and only if it commutes with the Laplace-Beltrami operator. So it sees the symmetries, how symmetric the manifold is. But typically, for non-isometries, you just take a homeomorphism or a diffeomorphism, and something that preserves the domain of the Laplace-Beltrami operator. The commutator is not even bounded. Not 0, but not even bounded. And when you want to use this operator to study dynamical systems like actions of non-isometries from the manifold, having unbounded commutators, it's not very useful. Simply because this commutator, in principle, it should be the analog of gamma prime, the derivative of gamma. Which means that non-isometric actions are not differentiable with respect to this Laplace-Beltrami operator. But if the commutator was bounded, they would be differentiable. And the question is, well, first, can we make sense of a Laplace-Beltrami operator on general Ahlfors spaces? And second, can we achieve for this generalization that delta, this generalization with gamma, where gamma is maybe a non-isometry, is bounded, a commutator? The answer to the first question is no. We cannot generalize the Laplace-Beltrami operator as it is on general Ahlfors spaces. The reason is that the Laplace-Beltrami operator is a local operator, which means that if you take a function f, then delta f will have support close to the support of f. But this cannot happen for totally disconnected spaces like the Cantor set, because it cannot meet metrics and the Bernoulli measure, for instance, for which it becomes Ahlfors regular. And the reason is that you have characteristic functions which are continuous in these situations, and they will be locally constant and in the domain of such an operator, and therefore you cannot have a local operator because of the existence of nice characteristic functions. This means that we need to think of non-local operators as generalization of the Laplace-Beltrami on Ahlfors spaces. And the second is, can we achieve that delta is bound, the commutator of delta with gamma is bounded? The answer to this is yes. But one needs to consider non-local operators whose eigenvalues grow slowly to infinity. These are unbounded operators, positive operators, and we want their eigenvalues will grow to infinity. We just don't want them to grow very fast. In fact, if they grow logarithmically fast, then we can have yes to both. Pick a non-local operator with logarithmically growing eigenvalues. Please stop me whenever you want to ask anything. Okay, so here's the candidate, and then I will try to convince you that it's exactly what we need. All right, so the idea is the following. We consider a bilinear form on densely defined on L2 of the Ahlfors space, and it's given by this formula. And it's densely defined on this space, which can become a Hilbert space if you consider this inner product here. Now, probably you might have seen this formula before, but not as it is, but with some plus alpha here, some small alpha, delta plus alpha. And this is related to fractional Laplacians on the Euclidean space. Okay, but you can also make sense of those on metric measure spaces if you have a nice enough measure with some control. People had not studied the case alpha equals 0 because it just behaves very, very differently. And in fact, most of the tools that over the years people developed for fractional Laplacians do not really work whenever you put alpha equals 0. It's a very singular situation. And out of this bilinear form, then using Rie's representation theorem, then you can have a densely defined positive and self-adjoint operator, which I will denote by delta again here on L2, so that this bilinear form is really given by the inner product in L2 of the square root of delta. Apply that F and apply that G. And this is what we call the logarithmic Dirichlet Laplacian. What I should say here, like highlight, is that it is not trivial, definitely, but a lot easier to study the square root of delta, and therefore, which is equivalent to studying this bilinear form, which is Dirichlet form, and a lot more difficult to study delta on the nose. The reason is that if you have the form applied at f comma f, okay, then it's going to be a positive number, and you see here that the formula is given by f of x minus f of y squared, okay, if you have f equals to g. And so when you have an integral where the integrand part is positive, then you can do inequalities easily enough. And this makes it already a lot easier to study the form. But if you go to the operator delta, then you can see that it has this formula here, and which might be a negative or positive, it becomes a lot more tricky. And therefore, it's more difficult to do analysis. Okay, going back a bit, why do we call it logarithmic? Well, because this is a singular kernel, and the singularity is of logarithmic order, okay? Right. Okay, so we have this logarithmic Sobolev space and the form, and using the Rie's representation theorem, we obtain a generator. It's called, or this positive self-adjoint operator delta that gives back the form. And kind of immediate proposition is that the kernel of this generator, that we will call now the log-Laplacian, is really the constants, and the image of delta is in fact closed, and it's given by all the functions of 0 mean on L2. And moreover, the domain of delta, it's an unbounded operator, it's pretty big of this one. It contains all Dini continuous functions. All holder functions of any exponent between 0 and 1 are Dini continuous. Okay, do you know what Dini continuous function is? You have the modulus of continuity of a function, which is a function over t, where t is from 0 to 1, and you want the modulus of continuity as a function of t divided by t to be integrable. That's a pretty big domain. And the reason is that the singularity is logarithmic. This makes the domain pretty large. Alright, so this is the operator I want to talk about, and let's see several examples, how it behaves. It took us a lot of time and was a very challenging problem to study this operator on the nose. And people were interested about this operator in non-commutative geometry because they wanted to define notions of differentiability on less regular spaces in dynamical systems. And it looks like this operator, the log-Laplacian, gives a unifying scheme for many other known situations. Okay, so how does it look on compact Riemannian manifolds? Again, X is a compact manifold, D is a Riemannian distance, and mu is the volume measure. And if you restrict the log-Laplacian on Lipschitz functions, let's say, you can write it like that, as I showed before. Now, this operator on the Lipschitz functions only was studied, has also been studied by Magnus Goffeng and Alexander Ishachev. And one using heat kernel asymptotics for the Laplace-Beltrami operator or Fourier analysis, then it is possible to show that the log-Laplacian is a bounded perturbation of a multiple of the logarithm of the Laplace-Beltrami operator. So you have the Laplace-Beltrami operator, it's a self-adjoint operator. You can do functional calculus. You take the logarithm of that, okay? It's still an unbounded operator. And now delta is what I write here plus a bounded operator, which really comes from the heat kernel asymptotics, because after some point you get bounded terms. What is interesting here is that this constant in this is like topological only. It doesn't depend on the Riemannian distance or the volume. Now, from this compact perturbation, we get that the log-Laplacian is essentially self-adjoint on Lipschitz functions, because this is essentially self-adjoint on Lipschitz functions. Moreover, delta has compact resolvent, meaning that you can find, you can diagonalize delta on L2. Its eigenfunctions will give an eigenbasis for L2, and its eigenspace is finite dimensional. Okay, and now the logarithmic behavior of the eigenvalues. So on the circle, the eigenvalues grow like n squared. So if you take the log of that, it's really the log, right? It's log n. Then you see that e to the minus t delta, this is the heat operator from the heat semigroup over t, is compact and trace class whenever t is greater than the topological dimension of the manifold over the volume of the sphere of dimension of the manifold minus 1. And this is sharp. It's trace class for t if and only if t satisfies this inequality, and it is not trace class here. And this means that the heat kernel, so this is an integral operator, and the kernel of this integral operator does not behave nicely for small t, for small time, but after some time it's nice. Now you might wonder, why should we care about something that gives a bad heat kernel for small t? Well, you cannot have everything in life. I will explain in a bit that this operator behaves nicely with conformal actions. And if you want an operator to behave nicely with conformal actions in your space, you cannot expect it also to have a good hit kernel all the time.
What do you mean, gives nicely?
It gives bounded commutators. Okay, so with this log-Laplacian, we recovered basically the Laplace-Beltrami operator. Let's see the other extreme.
So conformal is equivalent to isometry in the Riemannian.
Yeah, but they don't need to be isometries.
Yeah.
Yes, and that was a problem in the geometry, that you couldn't build the so-called spectral triples for non-isometries, but with that you can. On the other side of the spectrum, like manifolds and totally connected spaces, I just write here one of the easiest. Totally connected spaces, you take this counter set of infinite words of 0 and 1, you put the Bernoulli measure on it, and this ultrametric that counts for how long two sequences are the same. Now this is Ahlfors regular of dimension 1, and then you can diagonalize this operator on the nose, and the eigenspaces are really are given by wavelets. Wavelets are really a wavelet basis is really an L2 basis of functions that integrate to zero, of zero mean. And the way to build them here is that you view 0, 1 as the boundary of the dyadic tree, and then at its level, because the first level of the dyadic tree corresponds to the cylinder set of 0 and the cylinder set of 1, then of 0, 0, 0, okay, and grows like 2 to the n. And now you consider the characteristic functions on each level and the vector space that they span on each level. These are finite dimensional spaces, and one is a subspace of the next, okay? So you take projections, Qn, let's say you take the Qn projection onto the level n vector space of characteristic functions, and since it contains the previous vector space, the Qn minus 1, then you define Pn to be Qn minus 1, so the complement projection. Maybe I should write it
So
down.
is this a particular case of the spectral triple by Grissels and even?
Yes, you get, this is even spectral triple. This, after diagonalizing, we recover the Putnam-Julian spectral triple. But if you have this integral formula here, I mean, you cannot tell that you get this spectral triple. So you need to diagonalize, and you see that's what they had done. So what I mean is you have the dyadic tree, and you take a projection Q1, you take here the projection Q2. These are projections from the L2 of the shift of X with image the span of the characteristic functions of the cylinder set C0 and of C1. Okay? And this is from L2 to the span of the characteristic functions C01, C10, C11. And this is a subspace of that. And these are the projections. And in fact, you can show that this is also a projection. And this is what you define P2. And this is how you define Pn. And these then give the eigenspaces. You need to prove that. That's the idea. All right. right, so after diagonalizing, we can see that delta is essentially self-adjoint on Lipschitz functions because the wavelets are Lipschitz. Essential self-adjointness, it's not easy property to show in general. It's very challenging in general. Now delta also has compact resolvent, well, because you can see here these eigenspaces are finite dimensional, and the Hit semigroup is trace class if and only if t is greater than 2 times log 2. Now you can do this more generally. What you will get here is a topological constant that depends on the number of symbols and the topological entropy, the logarithm of the Perron-Frobenius you will get. Okay, so it looks like it is something dynamical, this threshold. And again, the Hit kernel is bad because, well, you get trace class after some point. Okay. Now,
so when you say more generally, you mean just a symbolic space with more symbols?
yeah,
and
it is
then you perform measure on it?
subshifts of finite type.
Okay, okay.
You take the parity measure. Okay, now the unit interval. Now you might wonder why the unit interval. We know how to integrate. Well, the closed unit interval, we know that the actual Laplacian, it's not self-adjoint there because you have boundary conditions. However, and that was an example that really made us pursue this log-Laplacian further, its properties. Because the log-Laplacian, it just works just fine on closed intervals. Simply because it sees the intrinsic structure of the space. Now, what happens here? You take the closed interval, Euclidean distance, and the Lebesgue measure. And you try to diagonalize the operator, this integral formula. Now, how do you do that? Well, you try to compute the log-Laplacian on this x to the n, okay? And then use this school property, okay? And if you look again in the formula, you put here x to the n minus y to the n, and then you can just break the integral so that you make it positive and negative parts, because here you would divide by the absolute value of x minus y, okay? Therefore you use that. Okay, and now recursively, you can start finding eigenvalues and eigenfunctions. The first eigenvalue here that you see is 1, okay? And then 3 over 2, 11 over 6, 25 over 12, and so on. Can you guess what these numbers are? Well, they are the harmonic numbers, each one. The harmonic numbers are the partial sums of the harmonic series. It's a harmonic number, well, 2 times of that, but that's really irrelevant. It's not important. The important is that all the harmonic numbers appear and they are simple eigenfunctions, like multiplicity 1. And out of this formula here for the interval, you have the harmonic numbers appearing. And you get that because of the logarithmic singularity that appears. So that was puzzling. And then we found a paper from the 1964 from Tak with you, who was studying fluid dynamics on slender bodies. And he had a formula in some appendix, a recursive formula for the Legendre polynomials. And it looks like he had used something similar without working with unbound operators and Laplacians. It's just a recursive formula. Had used something similar. And yeah, so it's quite puzzling how the harmonic numbers, like this number theoretic stuff, appear out of such a simple integral of the log-Laplacian. Anyway, so that's about the unit interval. Compact groups, not necessarily Lie groups, we don't need them to any smooth structure. So take, assume X is a compact group. Well, we have a finite measure and we want to use a Haar measure. And if the Haar measure is finite, then the group has to be compact. Then we can, without loss of generality, pick by invariant metric, left and right, and also the Haar measure. Then delta commutes with a convolution on the group, the convolution operation. And this means that you take the Peter-Weyl decomposition of the L2 space of the group, then delta is diagonal, acts by scalars on this decomposition. So it's a Casimir type operator that you find in Lie group theory. But no smoothness assumption is required here. And moreover, delta again is essentially self-adjoint on Lipschitz functions because of the above. In other words, the log-Laplacian behaves on groups as it should be. Okay, so far we have seen compact Riemannian manifolds, like totally disconnected spaces, spaces with boundary like the interval, compact groups, and this operator just generalizes all these well-known operators. Okay, so we were seeing, me and Bram Mesland, we were seeing this operator in our sleep all the time, for some time. And then we went to see the Oppenheimer movie. And it was a moment where they said in the movie that the Germans split the atom, and Oppenheimer was like, no, it's not possible. And then he goes on the board, he writes some math, and just for a second, they just show this board. I don't know if it's here now because there's light. They show this board. And immediately, I cut this formula there. So it's really something that looks like the log-Laplacian. I was like, what? There you have it there. Yeah, so if I read correctly, it's the electrostatic energy. So it's a formula, it's a Dirichlet energy. And it's no surprise that, Dirichlet forms appear there. But anyway, it was fun for us that we saw it in the movie also. So maybe it's not nonsense, everything that they write in the movies. Anyway, so these are one of the main examples I showed you, like these four classes, and these are the main general facts about the log-Laplacian. So indeed, it has compact resolvent, and its eigenvalues grow logarithmically fast. Moreover, its domain is a Banach module. It's a Banach space that has an action of the Dini continuous functions space, which is also a Banach space, a Banach algebra, in fact. And the action is continuous, so it's a Banach module, and that's interesting. Moreover, the commutators of delta with multiplication operators on L2, given by Dini continuous functions, are Calderon-Zygmunt operators, like integral operators with nice integral, and they are bounded on L2. And an interesting property is the following, that Lipschitz functions appear to be, well, they are in this infinite intersection. So you take the domain of delta and you take the domain of delta squared, becomes smaller, and of delta n you take the infinite intersection. So this is a Schwartz space, basically. C-infinity. C-infinity. This is the analog of C-infinity here. Okay? And you have that the Lipschitz functions are C-infinity with respect to this delta. And here's the interesting thing. Lipschitz functions, if you are on a manifold, they are almost everywhere C1. So you have something that in the classical sense is just C1, and with this delta becomes C-infinity. And the analog of C1 for this delta is the Dini continuous functions, this larger algebra. This means that if you are familiar with order of differential operators, the derivative is of order 1, the actual Laplacian, the Laplace-Beltrami is of order 2. This Laplacian is of order epsilon for any epsilon positive. So it's almost bounded, but it's unbounded. And this is a manifestation of that. And in fact, you can see it here in these computations. You differentiate, basically. You take delta on a polynomial of degree 2 and you get the degree 2 polynomial back. Okay, so it doesn't reduce the order. So, yeah. And now, all this, we're doing it because we wanted to study what is called non-commutative geometry of Ahlfors. Then I won't go too much into that for now, but the idea is that Ahlfors wanted to create a framework that you can use tools from differential geometry to less smooth situations, be it fractals or be it non-commutative algebras that you find in quantum physics. The fundamental tool really is a spectral triple, which encodes all the geometry. This is given by sister algebra A. Sister algebra is an algebra of operators on a Hilbert space, which is closed with respect to the operator norm and also closed under taking the adjoints. And we also want a Hilbert space, and we assume that A is an algebra of operators on that Hilbert space, and a self-adjoint operator with compact resolvent, like the one I presented you with. And now you want some compatibility between the algebra of functions, the observables, okay, and the operator D. It's that you want, it suffices to find a dense subalgebra in your sister algebra, so that the commutator with elements of delta of D with elements of the dense subalgebra makes sense and is a bounded operator. A prototypical example is really the continuous functions on a compact Riemannian manifold and C1 functions for the dense subalgebra. And then you consider the L2 space of differential forms, and then what is called a Hodge-de-Rham operator. And now, out of this triple, you can read back, you have encoded in this triple the Riemannian distance of the manifold, you can reconstruct it, the dimension of the manifold, the Euler characteristic of the manifold. So you get topology and spectral theory back. And the idea is that this also makes sense in the non-commutative setting, and that's why it's called non-commutative algebra, because you might have non-commutative sister algebras of operators. Like matrices. Matrices do not commute in general. Okay, and what we have is that for any Ahlfors space, the log-Laplacian together with the Dean continuous functions give a spectral triple. And in this generality, spectral triples have not been constructed before for commutative algebras. Okay, and now Kleinian groups, something more dynamical. You take the open unit ball in Rn plus 1 and you put the Poincare metric, and then it becomes the hyperbolic n plus 1 space. And then you consider the isometry group of that hyperbolic space, and elements from the isometry group, although they act isometrically on the hyperbolic space, on the boundary of the hyperbolic space, they act non-isometrically, conformally though. And then a well-known element that is associated to discrete subgroups of the isometric group of the hyperbolic space is the limit set of the discrete group. And the way to construct it is that you pick any point x in the interior, in the hyperbolic space, and you let it flow under the group action. And the action, no matter what points you start with, is going to accumulate on the sphere, on the boundary. And this is how you define the limit set. Now, we focus on convex or compact groups of second and first kind. These are some regularity conditions on the Kleinian group that allows you to equip the limit set with an Ahlfors regular measure, the Patterson-Sullivan measure, and also we assume.
Compact in relation with the bigger group. What do you mean for compact?
Not so. I do not necessarily mean that the quotient of the hyperbolic space by gamma is compact. I mean that there is a convex subset.
So it's about the action.
Yes, it's about the action. Yes. All right. So you have these Kleinian groups, and this is like a picture I could find on Wikipedia. Probably you have seen it. This is the limit set of some quasi-Fuchsian group. And going back to the corollary, that we have a spectral triple, we have differentiation on this kind of stuff. We have defined differentiation on these kind of spaces. Okay? In fact, I found online someone has created an app where you can put a Kleinian group and you get pictures from the limit set. So that's neat. Okay, so what do we really care? What's the very important property of this log-Laplacian for dynamics? It's really because if you take an element of the Kleinian group and consider its representation as a unitary operator on L2, people call this like Koopman representation. Then this representation preserves the domain of the log-Laplacian, and in fact the commutators extend the bound it wants. In other words, the action of the limit set, of the Kleinian group on its limit set is differentiable with respect to the log-Laplacian. This is what it says. And it cannot be differentiable with other non-local operators, like the fractional Laplacian.
So what is second kind? I don't remember.
The second kind is like the limit set is not the sphere. It's not.
Is it related to the existence of hyperbolic elements or something? Or no?
No, you can have also first kinds, which is the full sphere. I think you take the modular group, it's going to be a circle. For all these it works, so you get the same. I don't remember why I just put second kind here, but also for the first kind it works. And so this statement really means that we have a differentiation not only on the space, but also for the action of the Kleinian group on that space. So everything becomes differentiable. And the interesting thing is that this is intrinsically defined. We haven't used anything, just a metric measure structure of the limit set.
So sorry, but the fact that the system algebra is infinite depends on the fact that you choose second kind.
No, it's not necessary to be second kind. But the reason it's not important for the proof, the pure infiniteness here.
Yeah, of course.
It's really because pure infinite Caesar algebra is something very chaotic, let's say.
Yeah, I think
dynamical
you
system.
should have contracted
Yes, exactly.
stuff.
It's very something that it's hard to study its geometry, and here we created something that can study its geometry. So, all right, and then with this element you can do all sorts of stuff. First of all, you can study what's called the K-theory and K-homology of this algebra, which are topological invariants for the dynamical system, like homology theories for dynamical systems. You can also obtain KMS states. These are like equilibrium states for the dynamical systems. And other stuff. So, what time is it?
It's 10 past 12. So we have 35 minutes.
Ah, okay. Okay, do you want to make a short break, or how do you do it?
Isn't the second kind related with convergence or divergence of Poincare series? This is better. This is another property distinguishing.
Yes, yes.
Distinguishing claim.
Yeah, but yes, but what we want to, for this proof here, it's not important if it's second kind or first kind. I just put it to show, like, even for purely infinite situations, we now have a differentiation. Previous work on these kind of cross products, on people who work on defining differentiations, was Alain Kohn and Mathilde Marcoli. But as far as I know, they worked on Schottky groups, so the limit sets are zero-dimensional, and therefore you can do wavelet analysis. Okay? And now the way they defined their unbound operators was you take the wavelet basis and you pick the right eigenvalues, the eigenvalues that will give you an operator that you want to get at the end. And that's interesting because you create something in the framework of non-commutative geometry, but you cannot get more information that you started with. Whereas this operator here, it's intrinsic. We don't make any choices. We don't pick an eigenbasis and put eigenvalues.
So the measure here is something specific or any quasi-invariant probability measure?
Any Ahlfors, the Patterson-Sullivan or the Hausdorff measure. Yes,
Yeah.
exactly.
Variance is here not
No, it's not important.
adequate notion.
Yeah, yes, exactly.
It's Ahlfors.
Yes, You can just pick whatever you like. You have freedom. And moreover, you're not only for Schottky groups and not for Kleinian groups in, in S3. You have it for Sn. It's like n dimension.
We can conclude that the theory of the sister algebra with this approach.
Yes. Yes. But you need to add a potential. And that's why I'm saying Hamiltonians. This is a positive operator, and so its topological content, the K homology class, will be 0. And so what you do is you put a potential, a canonical one, dynamical, that alternates, makes eigenvalues like negative and positive, and you can do it in such a way that you recover K-theory classes back from Poincare duality. And I will show it that this works for topological Markov chains.
I don't think they computed the theory of, this is in result.
Yes. Yeah, you can do this stuff. So then I can move on to the next application of that. All right, so this is slightly more algebraic, but not too much. I will just put things under the carpet. The idea is that we really want to use this log-Laplacian to study dynamical systems. And we applied it with Bram Mesland and Magnus Goffeng on the study of the so-called Cuntz-Krieger algebras. These are very well-known sister algebras that are associated to finite direct graphs or to topological Markov chains, like subshifts of finite type, and encode their dynamics in some sense. These algebras have been widely studied since they were invented in the 1980s from Joachim Cuntz and Krieger. But studying their non-commutative geometry, equipping them with a structure, in geometric structure, it wasn't known. People had done some work here, more algebraic approaches, but not analytic ones that, I will come back to this slide, but not analytic ones that give new information about the Markov chains. And it was again picking wavelets, eigenbases, picking the eigenvalues, and hope you try to prove something by constructing the right thing. All right, so, but before going there, let me very roughly explain what is non-commutative geometry, or what some part of it. It's not really a theory, at least to my eyes. It's philosophy, basically. Yes, and has many interesting examples and many applications in many areas. But you cannot really define what it is. And the story really starts with the Gelfand duality in the 40s, which says that topological spaces, classical spaces, are determined by their algebraic structure of continuous functions, and they are in one-to-one correspondence with commutative sister algebras. Algebras of basically multiplication operators by functions on L2 spaces. And so if you have a topological space, you think of the continuous functions on it with the supremum norm. And if you have a commutative algebra, out of it, sister algebra, out of it, you can create a space using the spectrum, so that that space becomes a topological space, Hausdorff compact or locally compact, depending on whether the algebra has a unit or not. And now what people thought, why they pushed forward one reason to think of sister algebras was like, okay, let's drop commutativity. from the algebraic part, then what are the spaces that correspond to non-commutative Caesar algebras? And that's why sometimes Caesar algebras are referred as non-commutative spaces, topological spaces. Now, on the quest of finding non-commutative spaces, we often meet dynamical systems, group actions, and spaces. And as I write here, this is really a framework for Fourier analysis on dynamical systems. Simply because if you have a dynamical system and you consider the Caesar algebraic object associated to that, there's a way to do that, then most probably it's going to be of that sort. This is the analog of semi-direct product for groups, but now you have a group acting on an algebra. And the elements in here, okay, so this is some sort of completion, but really you consider elements, an element, let's say T, or capital F, let's call it. And here, which let's assume it's really the continuous functions on X, it's going to be written as sum over elements in gamma of some coefficients that depend on gamma and elements in gamma. So now the coefficients, so if you take X to be a point, then this is really the complex numbers, and therefore you get finite sequences, because you can assume that you take F to be of compact support. This is, let's say, a discrete group, so this is always a finite sum. Then you have elements gamma with coefficients. It's like polynomials. But now the polynomials we might have coefficients, continuous functions. Okay? And if you try to complete this to Caesar algebra, then you think of limits of this kind of polynomials. And non-commutative geometry puts differential structure on these spaces, and therefore it gives you basically subalgebras of these cross-product Caesar algebras of functions of elements where the coefficients, Fourier coefficients, decay fast enough. Okay, that's the rough idea. And this then unlocks many tools like differential structures. Then you can compute topological invariants for dynamical systems like zeta functions, heat trace asymptotics, and so on and so forth. Any question here? Okay. All right. And so we start with an n by n matrix of 0 and 1 entries and consider the topological Markov chain. So it's really a sharpshift of finite type associated to that matrix. You consider now the left shift map. It's one-sided words, so this is local homeomorphism, it's not injective, and the Patterson-Sullivan measure from the shift space. And now to this object, one associates the Caesar algebra, the Cuntz-Krieger algebra, which is really generated by n is the number of symbols, n partial isometries, Si, partial isometry, you can view it some sort of local homeomorphism, basically, at the level of spaces. And it really means that Si star and Si star and Si star Si, they are projections on Hilbert space. This is what it means. So it's generated by n partial isometries subject to the following relations. So you decompose the unit using these projections, the range projections of SI. Also, the source projections of SI are written in terms of the other range projections whenever this is allowed by the agency matrix. And the range and source the range projections for all those different isometries and the source projections, the range projections, they are mutually orthogonal. Now, on these sister algebras, as I told you, you have, and on sister algebras in general, you have homology theories and cohomology theories, like this exotic stuff. In more dynamical terms, the K-theory group, one of the K-theory groups of this algebra is the Bauern-Franks group. It's Z2, so you have that, the K0 group of FA, this Bauern-Franks group. Transpose for flow equivalence. And you have something to K theory, you have a dual theory, the K homology. And the following holds. Poincare duality in K theory. It's really an isomorphism between the K theory of this Cuntz-Krieger algebra to the K homology to the dual algebra, as you have it's really a non-commutative analog of Poincare duality for smooth manifolds, where here you have the homology of a manifold and the cohomology, the de Rham cohomology, and you also observe it in this framework. So in that sense, OA is somehow a non-commutative, not only a non-commutative space because it's a sister algebra, but of a dynamical system, but as a non-commutative manifold. With the log-Laplacian, we will make it a non-commutative smooth manifold. Okay, then that's a step after that. All right. So we want to access a bit more the structure from a more dynamical perspective, the structure of these graph sister algebras, the Cuntz-Krieger algebras, using Taylor equivalencies. The idea is that you consider here what is called a groupoid, which is like a space with partial multiplication, and you consider sequences x and y that they are right tail equivalent but with lag n. Okay?
This is exists K or for all?
Exists K,
Okay.
so that for that n you have that. So you take 0 n equals 0, it's really at some point x and y are the same on the right, so it's tail equivalent. But here you allow more freedom and you have tail equivalence with lag. And now the partial multiplication you can define here is simply the following. You can multiply x and y with something that starts with y necessarily, and then m and z can be whatever. And this is a multiplication. And now you can put a topology on this space, and the basis sets are given as follows. You consider you fix finite words alpha and beta, and then you consider all the infinite words x that start with alpha, they are in the cylinder set of alpha, all the words, infinite words y that start with beta, and if you shift them by the length of alpha and by the length of beta, they are equal. Okay, and this gives you a basis for the topology, for a topology in here. That
So in the definition of J, only 1k. You need only 1k.
Only 1k.
It's not from one point on.
Yes, and in the construction, it's important to consider the first k later on. That's a good point. But just 1k suffices, but it's useful to consider the first k, the first time.
This definition.
Yes, exactly. And now, the more geometric way to view this universally constructed Cicero algebra OA is to view it as an algebra of convolution operators on the groupoid, on the L2 space of the groupoid. So on groups you have convolution on groupoids also, wherever the convolution can be defined. And you send the generators Si, these partial isometries, to convolution operators by characteristic functions of those sets. These are the cylinder sets that start with the letter I, and you have n many. And this gives you a more geometric picture of OA. And this is what we are going to use. So, to give a differential structure on OA. And again, we have this log-Laplacian on the shift space. I remind you that it is a positive operator, essentially self-adjoint with compact resolvent, and gives a spectral triple for the continuous functions, sigma A. And you can just define it on locally constant functions, for instance. Okay. So, one point is that this groupoid, sorry, I'm going back, this groupoid now, the measure that you can put on that, it's not finite anymore, because it's locally compact, non-compact. And this formula makes sense for finite measures. So, you try to discretize canonically the groupoid as basically using some sort of Markov partition. So on the unit interval, 0 and 1, you can have, the decimals. Okay, this is a Markov partition, kinda. Well, in place of 0, 1, put the groupoid in this space. I won't go into details, but the idea is that you want to decompose the full groupoid into smaller parts of finite measure. And these are words, these contain like elements x and y, where x starts with alpha, y starts with beta, so it's like these basis elements before, but with some assumption, not assumption, with some other property, additional property. And now here I have alpha dot beta. So you make this decomposition over an index set, which consists of really finite words alpha, comma, finite words beta, basically. So the dot stands for comma, it's pairs. And you can have them whenever the last letter of alpha can be concatenated with the last letter of beta. So it's concatenation that you reflect the word beta. This somehow gives a Markov partition of the groupoid. And each such set, smaller set, is homeomorphic to the cylinder set of beta. Okay, and now it's possible using this decomposition to put a metric measure structure, an Ahlfors regular metric measure structure on the groupoid and define the log-Laplacian, and we get exactly the same formula that way, because you put the log-Laplacian on the L2 of its smaller set, you take the direct sum, and again, you make sense of that, but now you can make sense of that because this is an extended metric, in the sense that whenever x and y are in different components, the metric is infinite. So that's why you can make sense of this integral formula in an infinite measure space. Okay, and this is the spectral geometry of this operator, and you get quite interesting stuff. First of all, you can diagonalize it on the nose, and the eigenfunctions are Haar wavelets of dynamical origin now, because this groupoid encodes not only the shift space but also the dynamics on the shift space.
So sorry, does this debate before? Does this restricts to the one we defined before?
Yes.
It's true.
Yes. So it's an extension of that to the groupoid. Yeah, good point. So you get Haar wavelets. The eigenvalues also are computed on the nose, and they see a lot of the geometry of the shift space. They are written in terms of the transition probabilities of the directed graph. And moreover, now for the full, in the case of the full n shift, we managed, in fact, to write down, to find an explicit formula for the Hit kernel of the log-Laplacian on the groupoid. And this is something that you usually, I think that's quite new. Because usually you can write down explicit formulas for Hit kernels on very homogeneous spaces like Euclidean space or the hyperbolic space. Otherwise you would have asymptotic expansions, which are great. But here in the full shift, which is very homogeneous, you can write down an explicit formula for the Hit kernel that sees a lot of the dimension, the geometry of your space. This is a topological invariant, conformal invariant, and moreover, the Hit operators, they appear to be some potential operators, like from Riesz potential operators. I don't want to go into that. It's just some words that it's good if you know them, but otherwise they're not important for the talk. And moreover, one can start studying stochastic processes now on those groupoids using this Hit kernel and stochastic completeness and so on. So it's very explicit what you can do here. And how much time do I have?
Sorry?
How much time do I have?
10 minutes.
Well, it's fine. Great. Okay. Any questions here?
Maybe plenty. Lot of materials.
Yes. So, all right. That's about the main parts of the spectral geometry. As I told you, we have this algebra associated to a graph. So you have a topological Markov chain. Let's call it sigma alpha. And to this, you associate a a Caesar algebra. And we want to view this as a non-commutative smooth manifold. So we want to put smooth structure on it. And with the log-Laplacian, we can do that. And here I'm highlighting that it behaves as a differential operator should behave on an actual smooth manifold. You can study its its spectral geometry on the nose. You get Hit kernels, the eigenvalues have nice eigenfunctions, and also it's related to the question of Jacopo before, whether you can read the K-theory. So this operator, the log-Laplacian, also has information, topological information in it. In fact, you can recover all the homology group from this operator, all this, or the bound-Franks invariant. You can recover it. And this is not very important if you're not familiar with Caesar algebras. What I want to tell you is that you have this log-Laplacian, but you put a minus delta here, And now to this you add a potential. You create a Hamiltonian. And the potential is very explicit, you can just write it down. And now, this operator here gives a spectral triple for this non-commutative algebra. It means that the operator D has compact resolvent and commutation with functions from here with basically convolution operators, because now we have convolution, it's not only multiplication. Convolution operators with locally constant functions. They are bounded, the commutators of D and these convolution operators. And not just that, in fact, you can recover all the basic elements that generate the K0, so the Bauer-Franks group of the Markov chain, of the topological Markov chain, so these are classes of projections. You can write them down as Hamiltonians with the log-Laplacian.
Sorry, can you remind what is VA?
VA.
Beta and VA minus
VA. VA, finite words.
okay.
The finite words of any length.
Okay.
So here you create some kind of Fock space. And the Fock space is really all the information is in the Laplacian. The kernels of the Laplacian are really the constant functions, so like complex numbers here. And therefore, using the Markov partition, we can focus on the kernels of the Laplacians dictated from the Markov partition of the group population. And this gives some kind of Fock spaces. And if you project on those, you get these projections, and these give the potentials that you get all the topological information about your algebra. Anyway, I just want to show that it has information. And also, it behaves as it should be with isometries. As I told you before, the Laplacian and also the Laplace-Beltrami on a manifold and on a group, but also on a manifold, has the following property. The diffeomorphism of a closed Riemannian manifold is isometric if and only if it commutes with the Laplace-Beltrami operator. Here we don't have a closed Riemannian manifold, but we have something that a non-commutative object that we want to equip it with something that makes it a non-commutative closed Riemannian manifold. And we have this candidate, the log-Laplacian. Now, how do you make sense of the isometric group of OA with the operator D? Well, you focus now on automorphisms of your sister algebra OA that corresponds to unitary operators U that act on the L2 space of the groupoid, and they preserve the domain of your operator and commute with that. So the isometric group is really all the automorphisms of OA that have this form for some unitary U that acts on the L2 space. So the OA is represented as bound operators in this space, as bound operators like convolution operators. And all those automorphisms that are conjugation by this unitary U, and this U commutes with your operator, create a group. Now it's possible to get a complete description. It's easy to see that this isometric group embeds into UN, the unitary group of and then and therefore you can see that it's a compact Lie group. And then you can get a complete description of the isometry group. And together with the spectral theory of D that I showed you before, with all the eigenfunctions, values that you can compute on the nose, then you can show that this isometry group is a compact Lie group, and in fact it's this semi-direct product. You take the automorphism group of the directed graph A, it's all the permutations basically that commute with the agency matrix A, and you let it act on the n torus, where n is the number of symbols of your shift of the topological Markov chain. And moreover, we know that isometries on a metric space have zero topological entropy. Okay, so another indication that this is the right object of differentiation on those algebras is that the isometry group sees a lot of the symmetry of the directed graph, but also the topological entropy of the isometries is zero. There's a notion of topological entropy of non-commutative topological entropy that extends the classical topological entropy.
So sorry, the action of Tn, is it true that you have an action of Tn on OA such that the stabilized points are the continuous functions on this boundary?
Yeah, so
Is it true?
it's not the gauge action, because the gauge action is just T, the circle.
Yeah, exactly.
It's in there, the gauge action, in this isometry group, but we couldn't understand how Tn appears really, because it acts on the level of the algebra of OA, but we cannot see how it acts on the level of the groupoid or on the shift
You
space.
don't know the fixed point algebra?
No. We didn't check it, but yeah, I mean, there are more questions.
Because it seems like
check.
you are taking, it's a way to extend the isometry. This is what it seems to me. You have something like a fixed point algebra and you extend it to everything, and you're saying that the isometry is actually what you take. But
Yes.
maybe it's just a comment, yeah.
That's a,
It could be the case, could be the case.
yes, maybe, yeah, we can talk about that.
Okay.
What do I want to say? Yeah, so for instance, if you take the graph with agency matrix, this one, or this one, then the isometry group is going to be the n torus. It's going to be something commutative, something small. Okay? And if you have the full shift, then you have like t to the n by the full permutation group.
And in this case, OA is. In this case, OA is.
I don't remember if it's with that or without. As you Q2, you get models.
No.
No, as you Q2.
Okay.
Yeah.
The quantum is.
Yes, you get all this. Okay, so conclusion, there is a differentiation on these algebras, spectral triple, with properties on the heat traces that are related to equilibrium states for the dynamical system, and this is something that I intend to study. And closed formulas for heat kernels on the groupoids in connection with Riesz potential theory. You can recover the topology, the homology of those algebras from those Hamiltonian type operators like Laplacian plus potential, and also the isometry group recovers the symmetry of the underlying directed graph. And we hope this is a blueprint for general groupoid algebras, and this means for dynamical systems in general. Dynamical systems, you can convert them into groupoids. And the idea is that non-commutative geometry is to build you start with a dynamical system, you look at its sister algebra, and there you try to create a differentiation framework that contains a lot of information about the topology and the dynamics of the dynamical system, like zeta functions, stuff like that. Thank you.
Any questions?
I have two questions, if I can. The first one is if you could compute the dimension of the spectral triple in these cases.
Yes, yeah. You have it here. You mean this T0?
So in particular, yeah, who is T0?
Yes, so for a general subshift of finite type, I can give you an estimate, but not exactly. The reason it's like, I know that it's a constant multiple, a fixed one, times the topological entropy of the subshift.
Okay.
Now, if you give me a particular subshift, then I can work it out. But in general, yeah, it's difficult. The reason is that it's difficult to write down explicit formulas for general wavelets. But if you have like very homogeneous Markov chains, then you can do it. You know, probably it's doable, but haven't really worked it out. There were, even for the full shift, computations were way too many.
And for the case of compact Riemann surfaces, do you obtain the dimension of the manifold?
Probably.
The dimension.
Yes. For manifolds, you obtain dimension in the nodes,
Okay.
so you can work it out from here.
I see. And okay.
So this should be this threshold should be the inverse temperature for the KMS state, for the equilibrium, for some equilibrium state with respect to some flow on the space.
And the second question here. There is this notion of condistance between states.
Yes.
Can you compare the isometry groups of this spectral tree?
Yes, that's a good question. And the answer to that is that, where is it? Anyway, the answer to that is this spectral triple gives infinite condistance. So there's a dichotomy, it looks like. I haven't.
But okay, you can also preserve it. I don't know. There are some
Sure.
points with fine.
Sure. Yeah. Probably yes, but it's not very meaningful, I feel, if you have something infinite. And the reason is the following: so in here the dynamics are not isometric. You have the shift acting, so it's non-isometric.
I see what you.
And so you have this conformal action. You cannot expect, and then you have an operator, differential operator, basically, pseudo-differential, that sees some of the geometry. Now, if it sees a lot of the geometry, then and also is compatible with the conformal action, this cannot happen. So it sees from the geometry of the space only its conformal part, and that's why you get infinite condistance. Now, if you want to see the condistance on the nodes, you need to consider the fractional Laplacians. These allow you, although they are non-local operators, they allow you more, they give you more global data on your space. And Therefore, they're not compatible with general conformal actions. And this can be proved, in fact. The commutators with a non-isometry, like here, if instead you had the fractional Laplacian, the commutators would be unbounded.
So maybe it is reminiscent of pure infinite.
Yes, that's one way to prove it, but also you can do computations and see that it blows up. But it is in par with Cohn's obstruction of pure infiniteness here, because the fractional would give, finitely summable stuff.
More questions?
I have a question. So, is it reasonable to think about similar stuff for slightly less regular measures than Ahlfors?
Yes.
So maybe the measure of Ball scales as it should for almost every point, or things like this?
Yes. Yes, you can do stuff. You think about parabolic elements.
Maybe, or yeah.
So you can think. So whenever.
What do you mean by the symbol similar? Ratio power?
Uniformly.
Ratio of logarithms.
Uniformly, so you have two uniform constants, C1 and C2.
Okay, so this is very strong. This is
Yes.
true for hyperbolic.
Yes. But you can
make it weaker. Logarithm measure divided
Exactly.
by logarithm r equal to.
Exactly. You can do that. Yes. You can do.
It should work.
Yes, it should work. The reason that we focused on this was because we did what we wanted to do, and also to give something presentable. If we did it in full generality, it would be very complicated. But yeah, already in non-commutative geo, the only thing that would change if you make this weaker is so the same techniques will work. Where is it? Is that this stuff here that you will not have these kind of thresholds. You'll have other kind of thresholds. It will change how the growth of the eigenvalues goes to infinity. How the eigenvalue, yeah. Anyway.
For example, on the
growth rate.
On the symbolic space, you could work with measures, let's say Bernoulli other than uniform.
Yes, you can do this stuff more generally, and maybe you can even add potentials, and you can do stuff. Yeah. So that was. We wanted it to be a blueprint of some sort, or food for thought. Yes, good point.
Thanks.
Some more questions?
Maybe online. Are there questions online?
Online, yes.
No, doesn't seem so.
Okay.
Oh,
Thank you.
thank you very much. Next week, we'll speak.
Was I on time?
Yes.